Okay. Now let's continue with other non-determinations. Okay, let's discuss the case 1 over 0. If we look in our list, we see that 1 over 0 is an exceptional case, so we need a method. Let's see first an example of a limit which is in this case. For example, when we compute limit when x tends to, let's say, 1 of x plus 2 over x squared minus 3x plus 2. Now, if we replace x by 1, we shall get, as usual, we shall get 3. We replace, the first thing to do at the limit is to replace x by, in this case, 1. So 3 over 0. This is the case 1 over. When we say 1 over 0, here above 1 is a generic number for something which is not 0. So attention, the case 0 over 0 is different. But here we're talking about the case when above we don't have 0. For example, we may have 3. And below we have 0. Okay, what's the method in this case? Well, the method consists in 2 steps. The first step is to make a table of sign of the denominator. So the sign of the denominator. And the second step is to compute the limit from the left and the limit from the right. And the limit from the right. We shall explain what that means. And we shall use the following formal operations, which must be added to our list of formal operations. 1 over 0 with a plus here, nearby 0, it's infinite. And 1 over 0 with a minus here, it is minus infinite. We shall explain what that means. Okay, so this is the method. So the first thing to do when we see that we have this case is to make the sign of the denominator. That means a table of sign. We need a table of sign of the expression x squared minus 3x plus 2. Okay, now here we need to, we have our first lesson at the Rose class was about the sign of the quadratic function. We know how to do it. We compute delta, which is 1, which is positive. Then we compute the two real solutions, which are 1 and 2. So, and the rule says that here we have plus, here minus, here plus. So here I repeat, we applied the sign of the quadratic function. We have the theory, I repeat, in our first class of Rose. Okay, and now we did the first step. Now the second step, what it means to compute the limit from the left and the limit from the right, or the so-called side limits. The limit from the left means that x tends to 1 being strictly less than 1. So generally, when x tends to 1, it means that x is closer and closer to 1, but it could be from at the left, from the right, like this, then like that, then like that, then like that. So x can be less or greater than 1. When we take the limit from the left, it means that x is closer and closer to 1, but it is all the time strictly less than 1. This is the limit from the left. We shall see how we shall use this. Of course, now if we replace x by 1, we shall get 3, and below we get 0 because nothing changed. X tends to 1, the fact that it is less than 1 doesn't change the value, which will be 0. But now we go to the table of sign here, and we see here when x is less than 1 and close to 1. So that this means the following: x is very close to 1 and it is at the left of 1, so it is less than 1. On this table, we see that 1 is here. When we are close to 1 but at the left, the expression x squared minus 3x plus 2 is positive. When it is when x equals 1, it is 0, of course, but before that it is positive. So we shall put here, so this plus from here is coming from the sign of the denominator. And now we have this 1 over 0 plus, it's infinite. So you can think like this: it is 3 times 1 over 0 plus. 1 over 0 plus, according to this formal operation, it's plus infinite. So it's 3 times infinite. And now this is infinite according to another formal operation. So the limit from the left is infinite. Let's see the limit from the right now, because this is written here. We must compute the limit from the left, and we must compute the limit from the right. The limit from the right means that now x is greater than 1. So x tends to 1, it is closer and closer to 1, but is all the time greater. Let's see what happens. Of course, we shall get 3 over 0 because nothing changed, the values are the same. But now if we look what happens with the denominator when x is close to 1 and greater than 1, we see that it is negative. Attention, don't look here. Here we are not close to 1. Close to 1 means here. So this is negative. In the same way, by using now this formal operation, we shall get minus infinite. So the limit from the right, in this example, it's plus infinite. The limit from the left, the limit from the left is plus infinite. The limit from the right, it's minus infinite. Now, the theory says that if the limit from the left and the limit from the right are not equal, the limit doesn't exist. So limit is 1 of x over x plus 2 over x squared minus 3x plus 2 does not exist. The limit exists if and only if both the limit from the left and the limit from the right are equal. If they are equal, then yes, the limit exists and equals the common value of the two limits. This is the case 1 over 0. Just one other example. Consider limit when x tends to 1 of, let's say, x minus 3 over x plus 1 times logarithm of x. Okay, let's see what happens when x is replaced by 1. The first step, it's always this one. Above we get minus 2, and below we get, sorry, here, change a little bit. It was a mistake. It is x minus 1. Now, what happens below? When x is 1, x minus 1 is 0. So here is 0 times logarithm of 1 equals what? The logarithm of 1, we have a lesson about the logarithm. Logarithm of 1 is 0. So here is 0 times 0. That means minus 2 over 0. This is our case. Okay. Now we know the method. The first step is to see the value, the sign of the denominator. The denominator, it is this one, x minus 1 times logarithm of x. Now, the domain of definition of the denominator is x is positive because the logarithm exists if and only if x is strictly positive. So here, x belongs to the interval 0 infinite. Now, in order to make the sign of this expression, we need to know where it vanishes. the equation x minus 1 times logarithm of x equals 0 has one single solution, x1 equals 1, because both factors vanish at x equals 1. So here is 1, is 0. And now here you can do it in two ways. Or to think to the sign of x minus 1 and the sign of logarithm of x, we must know them by heart, because we learn about the sign for the logarithm and the sign for the linear function. Or you can take a value from the interval 0, 1, for example 1 over 2, and check the sign of this expression at 1 over 2, which will be minus 1 over 2. So when x equals 1 over 2, we get here minus 1 over 2, logarithm of 1 over 2. And now please tell me, what's the sign of this number? What do you think is the sign of this number? Hmm? Minus 1 over 2 is negative, yes? So minus 1 over 2 is negative. This is negative. Logarithm of 1 over 2 is positive or negative? We must know the sign of the function logarithm of x. Logarithm of x means a logarithm with a base which is strictly greater than 1. We must know that if the base of the logarithm is strictly greater than 1, then the sign of the function, and we did it. You have in the first lesson of the rows classes, you have the usual functions in algebra. Among them is the logarithm. And there you have the sign, you have the graph. So the sign of the logarithm when the base a is strictly greater than 1, this is our case because here the case is e, is this one. Yes? So the logarithm has negative sign at the left of 1 and positive sign at the right of 1. So logarithm of 1 over 2, it's a negative number according to this rule. Again, we must know it. So minus times minus, that will be plus. So when x is less than 1, our denominator is negative. Now what if x is greater than 1? For example, if you take x equals 2, if you replace it here, you get 2 minus 1, that is 1, times logarithm of 2. According again to the table of sign of the logarithm of 2 is positive. So here we have plus times plus, it is still plus. Okay, so this is the sign for the denominator. Okay, and now we shall compute the limit from the left and the limit from the right. We get, when we replace x by 1, we get above minus 2, and below we get 0, of course. But now let's see, if x is less than 1, what's the sign of the denominator? It is plus. Minus 2 over 0 plus, it's minus infinity, and we met already this kind of operation. And now, when the limit from the right it is minus 2 over 0, and now we go to the table of sign for the denominator. At the right of 1, it is plus. So it is the same values, minus infinity. So because the limit from the left and the limit from the right are both equal with minus infinity, it results that our limit, remember our exercise asked to compute this limit. This will be minus infinity, because both the limit from the left and the limit from the right are both equal to minus infinite. Okay, if you have the, so here we need to complete tables of sign for the expressions which is on the denominator. Yes. But the usual functions, the sign for the function, we have them in the first lecture on the rows class, and it is recorded. You can find it here. If you have any questions, so this was the case 1 over 0. It involves the sign of the denominator and the limit from the left and the limit from the right. Okay, now the most common undetermination is 0 over 0, at least for functions. Yes, 0 over 0. Now, the usual method for 0 over 0, it is based on the derivative. So please tell me, do you know the formulas to compute derivatives, or you have a problem with computing derivatives?
I know it, but not well.
Okay. Now, computing derivatives. Okay, I see. So before continuing with the case 0 over 0, let's discuss a little bit about computing derivatives. Yes. Now, computing derivatives is based on two facts. First, you must know the derivatives of the usual functions, such as the derivative of a power is n times x at n minus 1. Attention here, this is valid not just for natural x, but also for other values. For example, if n equals 1, from here we get the derivative of the square root. X at 1 over 2 will be 1 over 2 times x at minus 1 over 2, which can be written as 1 over 2 root of x. So square root of x, derivative, it's 1 over 2 square root. So what I'm trying to say is that from here we can get a lot of other usual formulas. This is a very general formula. For example, all the roots can be derivated by using this formula. Okay, other usual formulas. The logarithm of x derivative, it's 1 over x times logarithm in the base e from a. Well, the usual case here is when a equals e, so the natural logarithm derivative, it's simply 1 over x. This is what we shall use in most cases, yes. Something similar holds for the exponential a at x differentiated. Now, the terms derivative and differential are equivalent when we can say we derivate, or we can say we differentiate. It means the same. I shall use both. This is a at x times logarithm of a. Of course, again, when a equals e, the exponential with a base e derivative is itself, is the function which doesn't change under the operation of differentiation. Other useful formulas. The trigonometric function sine of x derivative is cosine. Cosine of x derivative is minus sine of x. Yes. Now, most books of calculus have a table of derivatives, of usual derivatives. We can add to this one. Now, the derivatives of the inverse trigonometric functions, for example, arc sine of x, derivative it's 1 over 1 minus x squared. For the arc cosine, it's simply minus 1 over. Now, arc tangent of x, it's 1 over 1 plus x squared. If you remember, we use it when we found the power series of the arctangent and arc cotangent of x. Derivative is -1 over 1 plus x. This one, we already use it, I repeat, and this one also, when we found the power series of arcsine and of arctangent. Okay, other usual formulas. Well, for example, tangent of x derivative is 1 over cosine squared, and similarly cotangent of x, it's -1 over sine squared of x. Well, okay, these are the basic. Now, this is the first fact we need to know. The second is to know some formulas which involve several functions. For instance, we must know that if we take a constant multiplied by a function and we differentiate it, it is the constant times the derivative of f. So we say that the constants are going in front of the derivation. Now, if we have a sum and we need to compute the derivative of the sum, that is the sum of the derivatives. Yes. Well, for the product, it's a little bit more complicated. It's not that. If you have a product f of x times g of x, and you multiply, and you differentiate a product, here the formula is like this. It is the derivative of f times g of x plus f of x times the derivative of g. Okay? So this is how products are derivated. And finally, the last formula we need is the ratio. If we have a ratio and we want to derivate it, it is given by the following formula. It is the denominator is squared. And now above we have the derivative of f times g negative f of x times the derivative of g. Okay. So this formula, 4 formulas, is apply to the previous functions. For example, if we need to compute the derivative of root of x, 2 root of x minus 3 logarithm of x. We shall use at the same time these 2 formulas. Yes, the constants are going in front of the derivative, and the derivative of the sum equals the sum of the derivative. So we shall get 2 times the derivative of square root of x minus 3 times the derivative of logarithm of x. And now these derivatives, they must be known by heart from our table. So it is 2 times 1 over 2 root of order x minus 3 times 1 over x. Here we simplify and we get 1 over square root of x minus 3 over x. Yes, so the derivative of this function equals 1 over square root of x minus 3 over x. If there is any question here, please.
It is clear.
Okay, so you must know these formulas. And we still have one more formula, which is about the composition, the derivative of a composition of function. Now, first of all, what means the composition of 2 functions? If we have 2 functions, f and g, there is an operation, which, attention, this has nothing to do with the derivatives, first of all. It's totally independent. F composed with g at a point x equals, by the definition, f of g of x. For example, if f of x equals 1 plus x squared over 2 plus x at 4, and if g of x equals, let's say, x plus 3, let's compute both compositions, f composed with g and g composed with f. We shall see that they are not equal, so the operation of composition of function is not commutative in general, so they will be different. But let's compose them. So f composed with g at x is by the definition what's written here, yes, above. It is f of g of x. That means f of, so the first to be applied at x, it is g. It is this one. G equals x plus 3. So it is f of x plus 3. And now we compute f of x plus 3. F is given by this formula, but here is written f of x. F of x plus 3 means the following. Everywhere instead of x, we put x plus 3. So it will be 1 plus x plus 3 squared over 2 plus x plus 3 at the power 4. This is the composition f composed with g. Now let's see the other one, g composed with f at x. By the definition, this is g of f of x. So the first to be applied now to x is f. So that means g of f is this one, 1 plus x squared over 2 plus x at 4. Okay? Now we have to look to g. G of x is here, but this is applied to x. Now we apply it to this expression. So it's like here, instead of x, we have 1 plus x squared over 2 plus x at 4. So we shall get 1 plus x squared over 2 plus x at 4 plus 3. As you can see, they are different, of course. So this is how we compute compositions of functions. It's a very simple operation. Okay, but we have a special formula when we want to compute the derivative of a composition. And that formula, it is also called the chain rule. So the chain rule now, the chain rule says the following. If we have a composition, f compose, let's write directly, f of g of x, and we want to derivate it. This is the composition of f composed by g. According to the chain rule, this equals the derivative of f applied at g of x times the derivative of g. This is the famous chain rule. So here we have multiplication, attention. What that means? Well, it means that, for example, in our table of derivative, before we had sine of x, derivated its cosine of x. But what if here we don't have x, but we have an expression which depends on x? For example, we have sine of x plus root of x. This is the kind of question we ask. So we don't have sine of x. We have sine of somebody. That somebody is g of x. So according to this formula, it will be the derivative of the sine, which we must know it is cosine. So this is cosine, but applied to who? To whom it was applied. So cosine of x plus root of order x, root of order 2 of x. Now, the common mistake here is that people forget this factor. You must multiply now, the cosine must be multiplied by the derivative of g. The g is here, what is inside. So times the derivative of x plus root of order. Now it's good to put a parenthesis here to understand that this is multiplied, this expression is multiplied to cosine, not inside here at the argument of cosine. So it will be, that's why I shall write it in front. The derivative of this one, it is 1 plus 1 over 2 root of order 2 of x, square root of 2, times cosine of x plus 1 over 2 of x. So don't forget to multiply by the derivative of the argument. And so on. For example, we know that square root of x derivative is 1 over 2. But what if we have root of x squared plus logarithm of x, for example? Of course, we shall compute the derivative according to the same formula, the chain rule, yes? We must, attention, we never compute something, a derivative in this case, if we don't know exactly what formula we must apply. So we shall apply this formula written here, where f is the square root and g of x is what's written inside the square. This is g of x. So it will be the derivative of the logarithm. The derivative of this 1 over 2 square root of what is inside the logarithm, g of x. So x squared plus logarithm of x. And now don't forget to multiply with g prime. So the derivative of the expression which is inside the logarithm, the derivative of this one, which is 2x plus 1 over x. Of course, here we don't stop. Compute derivatives means, among other things, to obtain the simplest result. So here we need to compute and to see what happens. Yes, finally, to put it in the simplest form, that which is 2x squared plus 1, and below we have 2x times x squared plus logarithm of x. Yes, and this is the final result. Let's see, sometimes the computations are interesting. Let's see another one. Let's take logarithm of x plus root of x squared plus 1. Let's compute the derivative of this function. So it's a composition because the logarithm is not applied to x. The logarithm is applied to a function which depends. Something similar will be when we shall compute the derivative of the square root. It's not square root of x, it is a composition. It is square root of somebody. So here, this derivative will be, first we differentiate the logarithm. So that means 1 over x plus root of x squared plus 1. And now, according to the formula, we must multiply. I shall not write directly for this first exercise. Times the derivative of what is inside the logarithm. This one. This function is g of x from the formula from above, and this is the function f. So it is the derivative of the logarithm, 1 over what's written here, times the derivative what is written inside the logarithm. And now we have another exercise from the beginning. We need to compute the derivative of this function. So it is 1 over x plus root of x squared plus 1 times the derivative of this function is 1 plus, here again we need to derivate the square root but not apply to x, to somebody. So we shall proceed like here. It will be 1 over 2 root of x squared plus 1 times what? Times the derivative of the function which is inside the square root. So times 2x. Because the derivative of x squared plus 1, it's 2x. And now we need carefully to make the computations. 2 and 2 simplifies, so we get 1 over x plus the root. And here, when you amplify here by x squared, you will get root of x squared plus 1 plus x over root of x squared plus 1. And now you see a simplification, this one. So we've got this simple result. So we prove that the derivative of the function logarithm of x plus square root of x squared plus 1 is simply 1 over root of x squared plus 1. This is a usual computation of a derivative. Okay, tell me if you want to make other exercises with computing derivatives, or it's enough and now we can go back to our limits. Because there we shall, please.
I guess I can go back.
Okay, so it's enough about derivatives, yes? Okay,
Yes.
very well. Now we go back to the case 0 over 0. Yes. Now here we have a main tool, which is for most limits in this case, which is called the so-called L'Hopital rule. Now the L'Hopital rule says the following. Suppose we have the limit when x tends to some a. A is a number, or it could be infinite or minus infinite, of a ratio. And this ratio, when you replace x by 1, it is in the case 0 over 0 mainly, but also the method can be applied also in the case infinite over infinite. We discussed about this case already. We have already some methods. Those methods are very good because in those examples, L'Hopital rule doesn't work. But the main situation, it is this one. Some limits in infinite over infinite also are computing by using the L'Hopital rule. The most important is that it can be applied. So the L'Hopital rule can be applied only if we have 0 over 0 or infinite over infinite. If you have another case, don't apply it. Go to the method appropriate to that case. Okay, and what the L'Hopital rule says? Look, it says the following. If the limit of the derivatives, so if the limit of f prime over g prime exists, for example, it may not exist because, for example, the limit from the left and the limit from the right could be different. Yes, remember. But in most cases, this one exists. Then our limit, this one, equals the limit of the ratio of the derivatives. Actually, this is the L'Hopital rule. This is how we usually remember it. The fact that the limit of the ratio of the derivative exists or not, it's not in most exercises, 99% of the exercises, we don't have problems with this kind of situation. Yes. So, loosely speaking, L'Hopital rule says the following. If you have 0 over 0, then our limit will be equal to this one. And in most cases, this one is no more an determination. Similarly, if we have infinite over infinite, the method is very efficient for 0 over 0, and it is less efficient for infinite over infinite. What it means less efficient? In many cases, we obtain here a limit which is still in a non-determination case. Okay, but in the case 0 over 0, in most cases, the exercise is over once we applied the L'Hopital rule. Let's see some basic examples. Limit when x tends to 1 of x 3 minus 3x plus 2 over x minus 1 times logarithm of x. Okay, so first thing here is to replace x by 1 to see what you get. If we put x equals 1, we get 0 over 0. So this is our case. We go and apply the L'Hopital rule. According to the L'Hopital rule, our limit will be equal to the derivative of the numerator and below the derivative of the denominator. So below we shall have 3x squared minus 3. Below we need to differentiate a product. We shall apply the method, the formula for the product. It will be logarithm of x plus x minus 1 over x. I will leave it as it is. And now we have a new limit. So here, after we apply the L'Hopital rule, we started from the very beginning. It's like we have a new exercise and we try to solve it. What is the first thing to do when we have a limit? We replace x by, in this case, 1. If we replace x by 1, we shall get, above we get 0, and below we get logarithm of 1, which is 0, plus here is 0, so we get 0. Well, it's not very unusual that after we apply L'Hopital rule, we get again the same undetermination, 0 over 0. Yes, so it's not very uncommon. What to do? Well, here we have a new limit. Yes, it is 0 over 0. The theory says in the case 0 over 0, apply the L'Hopital rule, and we shall apply the L'Hopital rule. So what I'm trying to explain is that the L'Hopital rule can be applied at the same exercise many times. Yes. Now if we continue to apply the L'Hopital rule, we get above we get 6x, what we get below, it's 1 over x. And now attention, plus the derivative of this ratio. Here you need to differentiate a ratio. We have the formula. The denominator is squared. Here it's x minus x plus 1. So this one is this one. And here we have another limit, a new limit. What we do when we have a new limit, replace x by 1 here, and we get 6 over 2. So the limit is 3. So the idea is that once you have 0 over 0, apply L'Hopital rule. In many cases, this is enough. You get a limit which is no more an undetermination, but sometimes you may get another limit which is still 0 over 0. It's not a problem. Apply again the L'Hopital rule, and you will get the result finally. Let's see an example of a limit in the case infinite over infinite. For example, if we have limit when x tends to infinity of x squared plus x plus 1, and below let's put it x plus logarithm squared of x. Okay, this is infinite over infinite when we replace x by infinite. We know the limits for the logarithm, yes? The limit for the logarithm, the graph of the logarithm that we have, we already discussed about it in our first lesson at Rose classes. It looks like this when the basis is greater than 1. So here, that means the following on this picture. The limit at infinite of the logarithm is infinite because you see the graph is going up, while when x tends to 0, when x approaches to 0, the values of the logarithm are going down, unbounded. So the limit at 0, of course, x must be positive, it's minus infinity. These two limits are very important. We shall meet them many times, and you can observe them from the graph of the logarithm function. So now let's go back to our limit. It is infinite over infinite. So we shall apply The common factor doesn't work here very well because you have this logarithm and you cannot deal with logarithm, you cannot simplify. So L'Hopital rule seems to be more appropriate. So above we have 2x plus 1 and below we have 1 plus now the square root of the logarithm. Attention, here you have a composition to differentiate. It is something of the type of function u of x squared derivative. That means, so the function f is the square, is the square, and the function g of x in our general notations is the logarithm. So this is 2 times the function of x times u prime of x. So this is 2 times logarithm of x times the derivative of the logarithm, which is 1 over x. Okay? Here, I shall put the common denominator, which this one will be below. We have x plus 2 logarithm of x, and above we have 2x squared plus x. This is still infinite over infinite. Don't worry. Apply the L'Hopital rule, and we get 4x plus 1. Below it's 1 plus 2 over x. Well, this time when we replace x by infinite, we shall get above we get infinite, below we have 1, so the limit is infinite. This limit in the case infinite over infinite cannot be computed with a common factor because the logarithm cannot be simplified and so on. So here the L'Hopital rule is more appropriate. But all the other examples we solved at the case infinite over infinite cannot be done especially when you have roots of any order. By applying the L'Hopital rule, it's useless because the square root or the roots in general are more complicated when you differentiate them. Okay, if you have any question, please.
No.
Okay, if not,